Okay, we're going to talk about the alternating series test. I think previous video kind of cut out on me and I didn't realize that, so I apologize. So we'll pick it up with this alternating series test, which is going to be able to determine whether a series where the terms alternate in signs converges. This is the test itself. We have two ways of expressing an alternating series, and this little -1 to the n minus 1 or -1 to the n I usually just call the sign changer. And that's going to cause the terms to alternate. Of course, this one, the a sub n's here, we're going to think of as being positive. Okay, they're positive, and this -1 to the n minus 1, then when n is 1, if we're starting with n equal 1, is -1 to the 0 is positive 1. So the first term is positive, and then the next term is negative, and then the next term is positive, and so on. This one starts out n equals 1, -1 to the first power is -1. So the first one's -1, the second one's positive 1. So it's just which do you start with, a positive or negative term? But both of those are sign changers, and so this either of these series will converge if the a sub n, so in other words, take out the sign changer, just look at the absolute value, right? If those terms in this series that you're adding up, if that sequence of terms has a limit of 0 and the terms are decreasing for all n, then the series will indeed converge. Okay, now some of you might be thinking that, these are kind of weird. Aren't these going to always happen together? If the limit is 0, isn't this always going to be true? Well, that's not really true. You can come up with a sequence where the terms are still sort of bouncing back and forth. They're not strictly decreasing, yet you're still getting closer and closer to 0. Okay, and so you want to make sure both of these conditions are met. Now, why does this really work? I'll just give you a quick illustration of this. Let's say the first term a sub 1 is positive. Okay, and let's just say a sub 1 is this value. Then we're going to add to that a sub 1 a sub 2 to get the second term in the sequence of partial sums. So the sequence of partial sums, remember, s sub 1 would be the same as a sub 1. S sub 2 would be a sub 1 plus a sub 2, and so on. But in this sequence now, we're going to add the actual sign changer in as well. So when I add a sub 2, okay, the a sub n's are all positive, but the sign changer then makes it negative. So if I add a negative number to this a sub 1, I'm going to be somewhere back here, right? So here would be my s sub 2. Okay, and then s sub 3 would be a sub 1 plus a sub 2 plus a sub 3. But then that a sub 3 added to s sub 2 is going to be positive. It's going to bring me back this way. However, because they're decreasing, that a sub 3 is not going to bring me all the way back, because basically this distance right here would have been a sub 2's value, whatever a sub 2 is, right? We're going backwards because of that sign changer, right? The second term is negative. First term positive, second term is negative. So s sub 2, the sum of a sub 1 and a sub 2, is going to be back here. But then a sub 3 is smaller than a sub 2, so a sub 3, maybe is going to be something smaller, right? And then if I add a sub 3 to s sub 2, I'm going to get s sub 3, okay? And then what's s sub 4? Well, now I'm going to add a sub 4, but a sub 4, because of the sign changer, is going to be negative, right? And we're going to come back, but a sub 4 is less than a sub 3, so I'm not going to come back quite as far. And you see what's happening as we proceed? We're kind of bouncing back and forth, a sub 1, s sub 2, s sub 3, s sub 4, and we keep bouncing back and forth, and we're bouncing back and forth around some value here. We're approaching, getting closer and closer to it, and that's the sum of the series. So the sequence of partial sums is approaching a limit, a finite number, and that limit will be the sum under these conditions. That's sort of the idea behind the alternating series test. As far as how to use it, then you just have to prove these two things. You have to have an alternating series. So for example, let's look with this one. This one, of course, this is the sign changer is -1 to the n minus 1, and we can see when n is 1, 1 minus 1 is 0. I get -1 to the first 0 power is 1, so I get 1, n is 1, and then I get the second n is 2, I'll get -1 to the 2 minus 1, that's -1 to the first power, so there's my negative, and it's going to be 2, 1 over 2, so -1/2, and then +1/3, and then -1/4, and then +1/5, and then -1/6, and so on. And this is the alternating harmonic series. So it turns out this is going to be convergent, and this expression really can be thought of as -1 to the n minus 1, and then the a sub n's that we're talking about being positive. What's the a sub n? The a sub n is 1 over n. And so this is what we use in these two criteria. So number 1 we see is the limit as n goes to infinity of a sub n. Is that 0? Clearly it's 0. All right, as n goes to infinity, that's clearly going to 0. And number 2 is a sub n plus 1 less than or equal to a sub n. Well, if I plug in n plus 1, I'll have 1 over n plus 1. There's a sub n plus 1. Is that less than or equal to 1 over n? Yes, for all values of n greater than or equal to 1, that's going to be true, because the denominator here is bigger than the denominator here, so this fraction is smaller than this one. So those two conditions are met, and so by the alternating series test, this series that we're looking at, -1 to the n minus 1 over n, converges. But realize if I say, is this series absolutely convergent? If I took the absolute value of these terms, what would I get? I get 1 plus a half plus a third plus a fourth plus a fifth plus 6. That's the harmonic series, and we know that is divergent. And so this series is conditionally convergent. Okay. So the absolute value, it's not absolutely convergent, it is conditionally convergent. But the alternating series test is helpful for us in finding the convergence of such series themselves. Let's look at one more case with this alternating series test. This series alternates, and the a sub n part is right here. There's the sign changer. And so we're going to look at number 1 condition, the limit as n goes to infinity of a sub n is the limit as n goes to infinity of ln over n. And if I look at this, the natural log of n is going to infinity as n goes to infinity, and n is going to infinity. So this is of the form, indeterminate form, infinity over infinity. So can we evaluate that? Yeah, I'll use L'Hopital's rule. And I'll take the derivative of the top function. The derivative of natural log of n with respect to n is 1 over n. The derivative of n is 1. And then as n goes to infinity, 1 over n is going to 0, and 0 divided by 1 is 0. So this is going to 0. Basically what we're saying is n goes to infinity, the natural log function is increasing without bound, but it's not as rapidly approaching infinity as n is. And so this ratio is getting smaller and smaller, approaching 0. But that's what we needed for number 1, so that's good. And then number 2 is a sub n plus 1 less than or equal to a sub n. Is that going to be true? So let's see. A sub n plus 1 would be ln n plus 1 over n plus 1, and a sub n would be ln n over n. Now this is a little trickier than the one we had before, and so trying to reason which is smaller, because it's not just the denominator. This denominator is bigger here than here, but the numerator is bigger here than here, and so it's not quite clear directly from this. But what I want to say is one thing, if we think about the function, I'll just say a function of x because we're used to seeing it. That's the same, natural log of x over x. So this function passes through all the points of our sequence of terms that we're adding up, the ln of n over n. And so if I can show this function is decreasing, right, then clearly this statement would be true, right? If I can show it's decreasing, then the terms are going to be getting smaller, all right? And so how do we determine a function's decreasing or increasing? We use its derivative. So let's just try that from Calc 1, right? Take the derivative of this quotient. So I'm going to use the quotient rule. You remember that? It's the derivative of the top function, which is 1 over x, that's the derivative of natural log of x, times the bottom function, minus the top function, times the derivative of the bottom function, x, which is 1, all divided by the bottom function squared. So if you remember that, right, that is the quotient rule. Okay, well clearly I can simplify 1 over x times x is 1, and I get up top 1 minus the natural log of x over x squared. Okay, now let's think about this. When is this function going to be decreasing? When its derivative is what? Negative. Okay, now this denominator is always positive, right? Again, we're thinking values of x are going to be greater than 0 because, I mean, obviously n is equal 2 to infinity, so we're starting with x equal 2. But if I look at the natural log function itself, just a reminder of that function, at 1 it is 0 and it's increasing on its domain. So this is the graph of y equal the natural log of x. Right, and then the good thing is when is the numerator equal to 0? Well, what value of the input will give me an output that is equal to 1? What input will give me an output? Natural log of what is equal to 1? Well, I hope you all know the answer to that and say it's e, right? The natural log member is the exponent. The logarithm is the exponent on the base, in this case e, needed to get e, right? The natural log of e would be the exponent needed to get e. E to what power equals e? E to the first power, right? So the natural log of e is 1. Okay, so this is going to be up top 0 when x is e. But for there on out, look at that. For values bigger than e for x, right? E again is about 2.7 something, right? 2.7 something. And for values greater than 2.7, the value of the natural log of x will be bigger than 1, right? Bigger than 1. So this expression here is bigger than 1 for x greater than e. And that makes this numerator negative. So this is less than 0 for x greater than e. And remember, e is about 2.7. And so clearly, this is going from n equal 2 to infinity. And we know, by the time we get to 3 on, these terms will indeed have this behavior. So this confirms, so we know that f is decreasing, and so we know that a n plus 1 must be less than or equal to a sub n, the corresponding sequence that passes through the points of this particular function here. So with those two things, right, satisfied, we can now say that the series that we started with converges by the alternating series test. Okay, so pretty easy test to invoke. Just need to show two things: that the limit of these a sub n's, the absolute value, right, without your sign changer, that those terms are going to 0. The limit of that sequence of terms is going to 0, and the terms are decreasing, and it has to be decreasing for some fixed value on, right? And so we're saying from about 2.7, so from 3 on, we're good to go. Those two conditions are satisfied. This series then converges. Okay, so we'll stop there, and hopefully you can practice some problems with that. This will again be useful later on, as our goal ultimately is to get to power series, and when we're checking the convergence at endpoints of those power series, we will often see the alternating series test come into play.